Hello, my name is Gary Beasley and I'm lead instructor for Central Carolina Community College. I teach the Laser and Photonics technology program. Today I'm going to talk to you about optical density. So optical density is a measure of how much light can be transmitted through a specimen or a substance. If we look at our slide here, we have some light coming in, some initial intensity coming into the specimen, is traveling a certain distance through the specimen, and we have some intensity coming out. In this case, as you can see, it's less amount. So some of the light is being absorbed in the specimen. And optical density is just a way of telling how much light is coming out versus going in. Really, optical density is a logarithmic function of the intensity of light being transmitted through a material. So the formula here you can see says optical density equals log base 10 of incident intensity to the transmitted intensity. Since optical density is a logarithmic function and it's a ratio of two intensities, then it's unitless. So there are no units associated with optical density. If we look at it as a logarithmic function then, if we have an intensity of 100 coming into a specimen and we have a transmitted light intensity of 10 coming out, then if we take the log of that, log of 100 to 10, we end up with 1. So an optical density of 1 means that you have a tenth of the light being transmitted through a material. If we have an optical density of 2, then 1/100th of the light is transmitted through the specimen. And if we have an optical density of 3, we have 1,000th of the light being transmitted through the specimen. So, therefore then, the greater the optical density, less light is transmitted through the material. So optical density is a way of quantifying the amount of light transmitted through a specimen. The greater the optical density, the less light is transmitted. A good application example for using optical density is in the selection of safety glasses. When you're trying to select what type of safety glasses you need for a laser, there's parameters that you have to consider. One parameter is the laser's irradiance. Another parameter is the wavelength of the laser and the maximum permissible exposure. For a laser with a given irradiance of E sub O and a desired MPE, the OD of the safety glasses must be at least log base 10 of the irradiance of the laser divided by the maximum permissible exposure. As an example, if you had 100 watt per centimeter squared irradiance and you had an MPE of 0.005 watts per centimeter squared, minimum OD that would be required for the safety glasses for this laser would be 4.3. Now let's look at the physics behind optical density. When light is incident on a specimen, all the light does not pass through it. Some of the light is absorbed in the material. The amount absorbed depends on different things: the type of material, the absorption coefficient of the material, and the thickness of the material. The absorption coefficient of the material is going to depend on many things also. It's going to depend on the material's atomic structure. It's going to depend on the types of atoms or molecules, the density of the atoms or molecules, and the wavelength of the incident light. So optical density is a measure of how much absorption is taking place in a material. So how is light absorbed in a material? Well, as the light travels through a material, it interacts with the atoms or molecules and vibrates through them. As you can see in this graphic, as a light wave interacts with an atom or molecule, it's going to vibrate through it. As it travels between atoms and molecules, it's traveling at the speed of light. But as it's vibrating through an atom or molecule, it slows down in that process of vibrating through it. So the speed of the light is also impacted. And then as the atom or molecule absorbs the energy, and not necessarily all of the energy is transferred through to the next atom or molecule. Some of the energy is lost in absorption. So not all the light that travels from atom to atom is the same amount. So the absorption process is taking place. So unless the atom's energy levels line up for total absorption, some light passes through through the material. Some energy from the vibrating wave is absorbed in this process. So that's where absorption is taking place. And as we've said, optical density allows us to measure that absorption. Optical density is also related to the speed of light in a material. Recall that refractive index of a material N is the ratio of the speed of light in a vacuum to the speed of light in a material. As the optical density of a material increases, the speed of light in the material is going to decrease, and the refractive index of the material is going to increase. So optical density is directly proportional to refractive index. So in summary, optical density is a measure of how much light can be transmitted through a specimen or a substance. Optical density is unitless, and optical density can be also considered to be a measure of the absorption taking place in a material. Optical density is wavelength dependent. Optical density is inversely proportional to transmittance. So therefore, the higher the optical density, the lower the transmittance. Optical density is directly proportional to refractive index. The higher the optical density, the higher the refractive index of material. And optical density can be calculated by taking the log of the incident light divided by the transmitted light of that specimen.